In mathematics, a continuous function is, roughly speaking, a function for which small changes in the input result in small changes in the output. Otherwise, a function is said to be a discontinuous function. A continuous function with a continuous inverse function is called a homeomorphism. Continuity of functions is one of the core concepts of topology, which is treated in full generality below. The introductory portion of this article focuses on the special case where the inputs and outputs of functions are real numbers. In addition, this article discusses the definition for the more general case of functions between two metric spaces. In order theory, especially in domain theory, one considers a notion of continuity known as Scott continuity. Other forms of continuity do exist, but they are not discussed in this article. As an example, consider the function h, which describes the height of a growing flower at time t. This function is continuous. By contrast, if m denotes the amount of money in a bank account at time t, then the function jumps whenever money is deposited or withdrawn. So the function m is discontinuous. History. A form of this epsilon-delta definition of continuity was first given by Bernard Bolzano in 1817. Augustin Louis Cauchy defined continuity as follows. An infinitely small increment of the independent variable x always produces an infinitely small change of the dependent variable y. Cauchy defined infinitely small quantities in terms of variable quantities, and his definition of continuity closely parallels the infinitesimal definition used today. The formal definition and the distinction between pointwise continuity and uniform continuity were first given by Bolzano in the 1830s, but the work wasn't published until the 1930s. Eduard Heine provided the first published definition of uniform continuity in 1872, but based these ideas on lectures given by Peter Gustav Lejeune de Riclet in 1854. Real-valued continuous functions. Definition. A function from the set of real numbers to the real numbers can be represented by a graph in the Cartesian plane. Such a function is continuous if, roughly speaking, the graph is a single unbroken curve with no holes or jumps. A function is continuous at a point if it does not have a hole or jump. A hole or jump in the graph of a function occurs if the value of the function at a point C differs from its limiting value along points that are nearby. Such a point is called of discontinuity. A function is then continuous if it has no holes or jumps. That is, if it is continuous at every point of its domain. Otherwise, a function is discontinuous at the points where the value of the function differs from its limiting value. There are several ways to make this definition mathematically rigorous. These definitions are equivalent to one another, so the most convenient definition can be used to determine whether a given function is continuous or not. In the definitions below, is a function defined on a subset I of the set R of real numbers. This subset I is referred to as the domain of F. Some possible choices include I equals R, the whole set of real numbers, an open interval or a closed interval here, A and B are real numbers. Definition in terms of limits of functions. The function f is continuous at some point C of its domain if the limit of f is x approaches C through the domain of f exists and is equal to f. In mathematical notation, this is written as in detail. This means three conditions. First, f has to be defined at C. Second, the limit on the left-hand side of that equation has to exist. Third, the value of this limit must equal f. Definition in terms of neighborhoods. A neighborhood of a point C is a set that contains all points of the domain within some fixed distance of C. Intuitively, a function is continuous at a point C if the range of the restriction of f to a neighborhood of C shrinks to a single point f as the width of the neighborhood shrinks to 0. More precisely, a function f is continuous at a point C of its domain if for any neighborhood there is a neighborhood such that whenever. This definition does not require any assumption on the nature of the domain. For instance, the function f is automatically continuous at every isolated point of its domain. As a specific example, every real-valued function on the set of integers is continuous. Definition: in terms of limits of sequences, one can instead require that for any sequence of points in the domain which converges to C, the corresponding sequence converges to f. In mathematical notation, Weierstrass' definition of continuous functions explicitly including the definition of the limit of a function. We obtain a self-contained definition. Given a function f as above and an element C of the domain I, f is said to be continuous at the point C if the following holds. For any number epsilon greater than 0, however small, there exists some number delta greater than 0 such that for all x in the domain of f with C minus delta less than x less than C plus delta, the value of f satisfies alternatively written continuity of f. IR at Ci means that for every epsilon greater than 0 there exists a delta greater than 0 such that for all xi. More intuitively, we can say that if we want to get all the f values to stay in some small neighborhood around f, we simply need to choose a small enough neighborhood for the x values around C, and we can do that no matter how small the f neighborhood is. F is then continuous at C. In modern terms, this is generalized by the definition of continuity of a function with respect to a basis for the topology, here the metric topology. Definition using oscillation continuity can also be defined in terms of oscillation. A function f is continuous at a point x0 if and only if its oscillation at that point is 0, in symbols. A benefit of this definition is that it quantifies discontinuity. The oscillation gives how much the function is discontinuous at a point. This definition is useful in descriptive set theory to study the set of discontinuities and continuous points. The continuous points are the intersection of the sets where the oscillation is less than epsilon and gives a very quick proof of one direction of the Lebesgue integrability condition. The oscillation is equivalent to the epsilon delta definition by a simple rearrangement, and by using a limit to define oscillation. If for a given epsilon 0 there is no delta that satisfies the epsilon delta definition, then the oscillation is at least epsilon 0. And conversely, if for every epsilon there is a desired delta, the oscillation is 0. The oscillation definition can be naturally generalized to maps from a topological space to a metric space. Definition using the hyperreal-Cauchy defined continuity of a function in the following intuitive terms. An infinitesimal change in the independent variable corresponds to an infinitesimal change of the dependent variable. Non-standard analysis is a way of making this mathematically rigorous. The real line is augmented by the addition of infinite and infinitesimal numbers to form the hyperreal numbers. In non-standard analysis, continuity can be defined as follows. A real-valued function f is continuous at x if its natural extension to the hyperreals has the property that for all infinitesimal dx, f minus f is infinitesimal. In other words, an infinitesimal increment of the independent variable always produces to an infinitesimal change of the dependent variable. Giving a modern expression to Augustin Louis-Cauchy's definition of continuity. Examples: all polynomial functions, such as f equals x3 plus x2 5x plus 3, are continuous. This is a consequence of the fact that, given two continuous functions defined on the same domain I, then the sum f plus g and the product fg of the two functions are continuous. Moreover, the function is continuous. Is 0 are discarded, as they are not in the domain of f per gram. For example, the function is defined for all real numbers x minus 2 and is continuous at every such point. Thus, it is a continuous function. The question of continuity at x equals minus 2 does not arise, since x equals minus 2 is not in the domain of f. There is no continuous function f. R that agrees with f for all x minus 2. The sinc function g equals x, defined for all x0 is continuous at these points. Thus, it is a continuous function, too. However, unlike the one of the previous example, this one can be extended to a continuous function on all real numbers, namely since the limit of g, when x approaches 0, is 1. Therefore, the point x equals 0 is called a removable singularity of g. Given two continuous functions, the composition is continuous. Non-examples. An example of a discontinuous function is the function f defined by f equals 1 if x greater than 0, f equals 0 if x 0. Pick for instance epsilon equals 1/2. There is no delta neighborhood around x equals 0 that will force all the f values to be within epsilon of f. Intuitively, we can think of this type of discontinuity as a sudden jump in function values. Similarly, the signum or sine function is discontinuous at x equals 0 but continuous everywhere else. Yet another example. The function is continuous everywhere apart from x equals 0. Thomae's function is continuous at all irrational numbers and discontinuous at all rational numbers. In a similar vein, Dirichlet's function is nowhere continuous. Properties intermediate value theorem. The intermediate value theorem is an existence theorem, based on the real number property of completeness, and states, if the real valued function f is continuous on the closed interval a, b, and k is some number between f and f, then there is some number c in a, b, such that f equals k. For example, if a child grows from 1 meter to 1.5 meters between the ages of 2 and 6 years, then, at some time between 2 and 6 years of age, the child's height must have been 1.25 meters. As a consequence, if f is continuous on a, b, and f differ in sign, then, at some point c in a, b, f must equal 0. Extreme value theorem. The extreme value theorem states that if a function f is defined on a closed interval a, b, and is continuous there, then the function attains its maximum, i.e., there exists c, a, b, with ff for all x, a, b. The same is true of the minimum of f. These statements are not, in general, true if the function is defined on an open interval, as, for example, the continuous function f equals 1, x. Defined on the open interval does not attain a maximum, being unbounded above. Relation to differentiability and integrability. Every differentiable function is continuous, as can be shown. The converse does not hold. For example, the absolute value function is everywhere continuous. However, it is not differentiable at x equals 0. Weierstrass's function is also everywhere continuous but nowhere differentiable. The derivative f of a differentiable function f need not be continuous. If f is continuous, f is said to be continuously differentiable. The set of such functions is denoted C1. More generally, the set of functions omega to the rails, such that f is n times differentiable and such that the nth derivative of f is continuous is denoted Cn. See differentiability class. In the field of computer graphics, these three levels are sometimes called G0, G1, and G2. Every continuous function is integrable. The converse does not hold, as the sine function shows. Pointwise and uniform limits given the sequence of functions such that the limit exists for all x in I. The resulting function f is referred to as the pointwise limit of the sequence of functions nn. The pointwise limit function need not be continuous, even if all functions fn are continuous, as the animation at the right shows. However, f is continuous when the sequence converges uniformly, by the uniform convergence theorem. This theorem can be used to show that the exponential functions, logarithms, square root function, trigonometric functions are continuous. Directional and semi-continuity. A right continuous function, a left continuous function. Discontinuous functions may be discontinuous in a restricted way, giving rise to the concept of directional continuity and semi-continuity. Roughly speaking, a function is right continuous if no jump occurs when the limit point is approached from the right. Formally, f is said to be right-continuous at the point C if the following holds. For any number epsilon greater than 0 however small, there exists some number delta greater than 0 such that for all x in the domain with c less than x less than c plus delta, the value of f will satisfy. This is the same condition as for continuous functions, except that it is required to hold for ex strictly larger than c only, requiring it instead for all x with c minus delta less than x less than c yields the notion of left continuous functions. A function is continuous if and only if it is both right continuous and left continuous. A function f is lower semi-continuous if, roughly, any jumps that might occur only go down, but not up. That is, for any epsilon greater than 0, there exists some number delta greater than 0 such that for all x in the domain with x minus c less than delta, the value of f satisfies the reverse condition as upper semi-continuity. Continuous functions between metric spaces. The concept of continuous real-valued functions can be generalized to functions between metric spaces. A metric space is a set X equipped with the function dx that can be thought of as a measurement of the distance of any two elements in X. Formally, the metric is a function that satisfies a number of requirements, notably the triangle inequality. Given two metric spaces in a function, then f is continuous at the point C in X if for any positive real number epsilon, there exists a positive real number delta such that all x in X satisfying dx less than delta will also satisfy dy f less than epsilon. As in the case of real functions above, this is equivalent to the condition that for every sequence in X with limit lim x n equals c, we have lim f equals f. The latter condition can be weakened as follows. F is continuous at the point C if and only if for every convergent sequence in X with limit c, the sequence is a Cauchy sequence, and C is in the domain of F. The set of points at which a function between metric spaces is continuous is a G delta set. This follows from the epsilon delta definition of continuity. This notion of continuity is applied, for example, in functional analysis. A key statement in this area says that a linear operator between normed vector spaces V and W is continuous if and only if it is bounded, that is, there is a constant k such that for all x in V, uniform. Holder and Lipschitz continuity. The concept of continuity for functions between metric spaces can be strengthened in various ways by limiting the way delta depends on epsilon and c in the definition above. Intuitively, a function f as above is uniformly continuous if the delta does not depend on the point c. Thus, any uniformly continuous function is continuous. The converse does not hold in general, but holds when the domain space X is compact. Uniformly continuous maps can be defined in the more general situation of uniform spaces. A function is Holder continuous with exponent alpha if there is a constant k such that for all b and c in X, the inequality holds. Any Holder continuous function is uniformly continuous. The particular case alpha equals 1 is referred to as Lipschitz continuity. That is, a function is Lipschitz continuous if there is a constant k such that the inequality holds any b, c and X. The Lipschitz condition occurs, for example, in the Picard-Lindelof theorem concerning the solutions of ordinary differential equations.